Okay, so first I would like to thank Dr. Lei Li for taking the time to speak with us today. Also, I would like to thank Srinivas for providing the logistic help on making this possible. Today, we're very glad to have Dr. Lei Li, who is now, I guess, officially with UC Berkeley, but physically at Carnegie Mellon, to speak at the Fishbowl seminar series. He's going to talk about fast algorithms for mining coevolving time series, essentially trying to make the connection between the data mining, machine learning type of work with dynamical systems. Dr. Lei Li is right now a postdoc at EECS of UC Berkeley and also a visiting researcher at Carnegie Mellon. His interest lies in the intersection of machine learning, statistical inference, and database systems. More specifically, he has been working on Bayesian inference on open universe probabilistic models, probabilistic programming languages, large-scale learning, time series, communication, and social networks. He has won a number of prestigious awards, including the ACM KDD Best Dissertation runner-up last year. He got his undergraduate training at Shanghai Jiao Tong University and his PhD in computer science from Carnegie Mellon in 2011. So without further ado, let's welcome Lei. Thank you.
Okay. First, I would like to thank Professor Le and Srinivas for the invitation. I'm very honored to speak at the seminar today. So today, I'm going to talk about mining coevolving sequences. So first of all, let me define what is coevolving time sequence. So coevolving here means we have correlated multidimensional time sequences, and often with joint temporal dynamics. And we will see a few scenarios where we can get such coevolving time sequences. So the first scenario is data center monitoring. And we know all the companies like Facebook, Google, they operate their own data centers. And in together, those data centers consume a lot of energy. For example, in 2011, all the data centers in the US cost about $7.4 billion of power. That's just the cost on the power, not including those costs on the facility side. And also worldwide, the data centers cost about 30 billion watts of electricity, and roughly equivalent to the output of 30 nuclear power plants. That's the figures from 2012 last year from New York Times. So the challenge here is often facility people, when they run the data center, they install a lot of sensors to monitor the data centers, including software sensors and hardware sensors, and there are tons of data generated per day. For example, a mid-sized data center generates 1 terabyte of data, and often those data there are very complex type of physical interaction among the data, and we want to discover patterns in those data so that we can control the data center to make it better utilize power in energy efficient way. So the second scenario is from environmental monitoring. Here the problem is, for example, in the drinking water system, we want to detect the leakage of the drinking water or even pollutions in the drinking water system. And the challenge is, of course, there are noisy observations, and the observation is quite large. And this is quite relevant to our everyday life. In 2010, there was some water contamination in a small town in California. And also, last year, there was an event in Texas as well. So the third motivation is in the animation, in the entertainment area, where we want to generate natural and realistic animations by using motion capture technology. of course, this is a huge industry, and such type of techniques can be used in both games and movies as well. The challenge here is due to the technology limit of missing values, and second, it is hard to define the natural needs in the straightforward way, and we want to generate as realistic motion as possible. Another motivation is in network security, where we want to detect anomalies in either computer network or online activities, like from the streams of user clicks, we want to detect the spam users. So let me summarize a few challenges in mining coevolving time series. Roughly, this challenge can be organized into three categories: pattern discovery, feature extraction, and scalable algorithm. Yeah, for pattern discovery, if we can find a good pattern, then we can do good forecasting, imputation, trying to recover the missing values, compression, trying to summarize the data in a compact way, and segmentation for the time sequences, and anomaly detection. Similarly, if we have good features, we can use those features to do clustering or search similar time sequences from the database. Now, of course, in all the scenarios I mentioned, the data are often large, so we want to have scalable algorithms by using parallel or distributed computing. So the outline of my chart goes as follows. I will first describe the forecasting and the summarization techniques, and then feature learning for time series. And then I will give a brief summary of other relevant results on time series mining, and then a few conclusions and future direction. Let me start with the motivation. Why this is a challenge in time series mining. So if we want to forecast the future values, often the traditional way is we assume that the data is completely observed. Well, there are cases where we don't completely observe the data. There are often missing values. For example, in the motion capture or in sensor. In the motion capture, we put markers on human body and then use cameras to check 3D positions of those markers. Well, due to the movement of human body, there are occlusions, or maybe due to the obstacles, physical obstacles, there are missing values as well. In the sensor monitor case, it's also reasonable that maybe due to the low battery or radio frequency error, there are missing values in the time sequences. So formally, we can define the problem of this. We are given a set of sequences. Maybe they are from M sensors of continuous monitoring, and in this data, there are often missing values. Sometimes there will be a blank out where we have completely missing value across all dimensions. And we want to find an algorithm for three tasks. Task one, to recover those missing values. Task two, to compress or summarize the data in a compact way. Task three, to be able to segment data into meaningful components. Of course, the ideal algorithm should match these two goals. Goal number one, it should be effective, meaning that the reconstruction accuracy should be as high as possible, or the compression ratio should be as high as possible. The second goal is scalability. We want the algorithm to be scalable to the length of the sequences. Where in the continuous monitoring case, we often have very long sequences of observation. So without going to the technical details, let me give you a preview of the results, which is by our proposed Dynamo algorithm. So this figure shows the reconstruction error on the motion capture dataset where we try to compare different models versus the increasing length of the missing values. Of course, with more missing values, it's more difficult to reconstruct the values. Well, our proposed Dynamo algorithm, here shown in red, performs significantly better than all the other methods, including blind interpolation, linear interpolation, and missing value SPD. So how we did that? Let me give you some intuition of the Dynamo algorithm. So basically, we exploit two characteristics in time sequences. The first is the correlation among multiple time sequences. For example, if we have markers on the left hand and right hand, there might be correlation among left and right. So if there are missing values on the right, we can possibly use the observation for the left hand to recover those on the right. The second characteristic is the dynamics or temporal moving pattern. We can use those to, based on the historical observation, we can identify the trend and then use the trend to predict whatever missing in the future. So a traditional way to capture both correlation and dynamics is through common filter, where common filter only works where we don't have missing values. So the idea is pretty simple. Suppose we are given positions of previous time ticks. We can estimate the acceleration, velocity, and the true positions. And then, based on the Newton dynamics, we can basically forecast the future positions. And in our Dynamo model, we use a linear dynamical system to model the observation sequences. Here, the X as the observation, possibly partially observed with missing values. And we assume those sequence of observations are generated from hidden variables here in Z. And we also assume there are linear dynamics for those hidden sequences with Gaussian noise. So in this model, we want to estimate the model parameters. Here we have 6 parameters for the initial condition, the transition dynamics, and the projection matrix, and the noises as well. And in addition, we want to recover those missing values and unobserved latent variables as well. So how we do the model learning? In short, we're trying to maximize the expected likelihood of the missing value and the latent variable condition on the observed value and the model parameter theta. We want to find the set of parameters theta such that it will maximize such log likelihood function. And our proposed optimization method use expectation, maximization, and recovery steps, and the iterations over these 3 steps to get conversion results. So now let me show you how we can use the same model to achieve not just forecasting, but also compression and segmentation. So how can we do summarization for multidimensional data? The traditional approach is through principal component analysis or singular value decomposition. The idea is pretty simple. Suppose we have a 2-dimensional data, body height and body weight, and instead of using 2 numbers to represent each data point, we actually want to use a single number to represent each data point. So now the idea is we can find a line and project the data point to this line, where this line is basically the principal component. And we can find such line with the method to minimize the reconstruction error, which will give the principal component and this result. And if we want to put it in a matrix way, we have the Bayesian matrix X. We want to decompose this matrix with two factors, U and V. And these two factors are often low dimensional or low rank. In this way, we can actually compress the original data into small low dimensional case. But why don't we use the PCA or SBD in time series data? So if we directly use the PCA or SBD, we can get some matrix, score matrix and loading matrix in this way, and it's a huge reduction of the storage. However, it won't achieve a high accuracy, high reconstruction accuracy. To be able to improve the reconstruction accuracy and also even achieve even higher compression ratio, we can use the Dynamo model. The Dynamo model basically has the initial condition here denoted in red block, in green blocks, and transition matrix in purple, and projection matrix is in yellow. So instead of storing the huge loading matrix and score matrix, we can just store this projection, small dimensional projection matrix and the transition matrix with a single vector of initial condition. However, this straightforward approach is very bad in reconstruction. So what we do is we try to use some synchronization point. So this is a simple idea of using the fixed sampling of the latent variables, where we keep some proportion of the learned hidden variables, and every while we use a full transition matrix to reconstruct the signals by using the synchronization point. So in this way, we can still achieve higher compression ratio than a singular value decomposition and even better reconstruction accuracy. But we can even do better. Instead of sampling at fixed rate, at a uniform rate, we can keep just some proportion and sample them dynamically. So in this way, we can achieve even higher accuracy, even higher compression ratio, and with almost the same reconstruction accuracy. So that's for compression. Now let me tell you how to do segmentation by using the same Dynamo model. So let me illustrate this idea by a synthetic example. Suppose we have a signal starts from a single frequency, then continues to another frequency. Now, of course, there's a change point here, and we want to identify the change point. So the idea is by checking the reconstruction error, we can find spikes in the reconstruction error, and we can detect those change points or boundaries by detecting those spikes in the reconstruction error. So let me show you some results of this. Yeah, sure.
Can you move 2 slides back? Go back to the. Can you move back 2 slides? One more. Can you give us a little detail about how do you compute that G and F matrices?
Oh, G and F. Okay, that's a very good question. So sorry, I omitted some details here. So the Dynamo model has 6 parameters, including the transition matrix F, projection matrix G, and the initial condition here, and the rest are just the covariance matrix. And the Dynamo try to maximize the expected likelihood, log likelihood, to find out the best set of parameters that can maximize this log likelihood function. So then we can use the expectation, maximization, and recovery algorithm to find out the parameters, and in the meanwhile, we can find out those latent variables.
How do you determine the number of latent variables?
Okay, again, that's a very good question. So I think we don't have a best answer, but we do have some practical guidelines. There's a Fukunaga principle which says if you can use your model to reconstruct the data with 95% of accuracy or 95% of energy, then basically we can choose the dimension with that threshold. So the way we choose the number of latent dimensions here is basically we try a few number of different latent dimensions, and then as long as we achieve the 95% threshold, then we stop at that number.
Maybe one more last question, sorry. So
sure.
Now your method should apply to nonlinear physical model.
Okay.
That's looking at dynamics.
Okay, the question is about nonlinear physical dynamical system. That's absolutely a very good question. In Dynamo, unfortunately, it assumes a linear dynamical system. We can't handle nonlinear dynamical system, and even worse, we assume Gaussian noise. And in reality, often we don't observe Gaussian noise. So to answer your question on the nonlinear dynamical system and also maybe non-Gaussian noise, I do have some ongoing work trying to use particle filtering to estimate the parameters in nonlinear dynamical system with non-Gaussian noise. But it's not solved by Dynamo.
Oh, okay, thank you.
Can I ask one more question?
Yeah, sure.
So there has been a lot of work on time series, EM algorithms, multivariate. Econometricians use this routinely for modeling lots of things. So does Dynamo break new ground in terms of theoretical method, or is it break new ground in terms of computational algorithm? What is the
contribution?
I mean, yeah, so I'm trying to put this in context.
Okay. So first, the Dynamo use actually the same linear dynamical system I guess proposed before in the literature. Linear dynamical system with Gaussian noise is perhaps well known. So that's not our contribution. Our contribution is to have a new algorithm that can estimate the parameters in the existence of missing values. And in addition, we try to achieve three goals with the same model. We want to do forecasting, we want to do compression, and we want to do segmentation. So all these can be achieved by the same model, same algorithm.
But the basic is methods like maximum likelihood. The basic principles are what we squared or maximum likelihood or things of that.
Yeah, the basic mathematical or model, you would say, it's known before, which is a linear dynamical system with Gaussian noise. Okay, let me back to the result. So again, this is the same figure we have seen before. Reconstruction of those missing values with the Dynamo method. And for compression, we also tested on, this is another dataset, which is the chlorine concentration level in drinking water system. There are many locations where we monitor the chlorine concentration level, and by monitor the levels, we can actually detect the freshness of the water. So if the chlorine concentration level goes down, maybe the water is not fresh at all. And in this case, we want to compress the data in a complex way, while our Dynamo method with optimal compression, optimal sampling achieve the lowest reconstruction error and the highest compression ratio. And for segmentation, we can show the example by anecdotal evidence. So here is one particular motion capture sequences where the sequences actually starts from running motion and then transition to a fully stop. And our Dynamo method can find the transition boundary denoted here in the middle. And by examining those the original sequence, we found out that those regions actually correspond to the region where the actor is actually slowing down. So it's meaningful. The result is actually meaningful in the real case. Now we have seen we can use Dynamo method to do missing value recovery. Can we actually solve the imputation problem with even better reconstruction error? So the idea is Dynamo perhaps it works in general case. It doesn't include a particular modeling of the domain. So what if we include the domain knowledge of some domain constraint into the model? And then can we improve the model reconstruction accuracy? So here is another model we propose. It's called bone length constrained occlusion filling. Basically, you exploit the skeleton of human body and try to impose the body constraint on the dynamical system. So the dynamical system will not only preserve the moving dynamics or correlation among multiple sensors or multiple data streams, but in this particular case, because we are working on motion capture data and those data are generated from human body skeleton, and we do know that those markers are attached to human bones. So for those markers on the same bone, they have a fixed length. So our proposed Bolero method will preserve the distance of those markers on the same bone, and it produces a very nice result. So if you are curious about the details of the Bolero, here are the optimization equations with the hard constraints and the soft constraints. And what we find out is Bolero with soft constraints works a little better than hard constraints. So that's all for the forecasting and the summarization. Next, I'm going to talk about feature learning for time series. So the motivation question is, suppose we have a database of time sequences. In this particular example, it might be, again, motion capture sequences. We want to find a sequence from the database that is most similar to the query motion. And the sequence, the result can be used to generate the natural realistic human motion or find some similar sequences to my queries as well. So a central problem here is how can we estimate the simulation among time sequences? So we can use we can directly apply Euclidean distance as a simulative measure on the sequences, on the raw data sequences. Or we can extract a few features and then apply the distance function on those features to compute the simulations. While here, our approach takes the second way. We extract a few features, but features can be the average or Fourier. But the features we propose in our work is, which we call fingerprints. And the underlying question is, how can we find those good fingerprints or good features? So our intuition is there are three criteria of good features. If we want to find really similar sequences, we want those features to be able to handle time shift and handle frequency proximity and handle grouping of harmonics. So I will explain them through some examples. Let me give you a preview of the algorithm. So our algorithm is called PLiF, parsimonious linear fingerprinting. So the results, the left one shows the features generated by the PLiF method. Two features generated on the motion capture data. Here we have running motion, walking motion and running motion, walking in blue and running in red. And on the right, those are traditional feature extraction methods by principal component analysis. Then we see that on the left, the running motion and the walking motion are pretty separated, while on the right, if we use the PCA features, they are pretty mixed together. So now let me give you some intuition about the fingerprints and the three requirements of the fingerprints. So suppose we have a few 5 signals here that are generated by one frequency and 2 other frequencies. So by capturing the time shift, we can actually discover that the first 2 signals, they are generated from the same underlying data generation process, but with different time shifts. And then the second property is the first and third signal are generated by nearby frequencies. And another intuition is some signals are generated by groups of frequency or groups of harmonics. So this is inspired by our human voice as we speak. The voice is actually composed of a mixture of sound frequencies. And then by extracting those basic frequencies or groups of frequencies, we can identify the weights of each signal on the frequency. Then if we project them into low-dimensional space, we can find better clustering. In this case, we can separate running motion from the walking motion. So why this way? Why PLiF will work in this way? It turns out that there's actually an underlying process governing the feature generation of PLiF. It's called complex linear dynamical system. So the basic idea is that the observation sequences are generated by a set of latent unobserved bases, while those basis function is corresponding to harmonics. While here, harmonics means it has a fixed frequency and it has either growing or shrinking or steady magnitude. But by using complex linear dynamical system, you can model the underlying frequency and their changing magnitude, and also find out their mixing weights. So to illustrate the idea of basis function, now suppose our 5 signals are generated by 2 sound sources. The first 3 are generated by a diapason. It has a pure tone with some noise. And then the last 2 are generated by a violin, which produces a set of frequencies, perhaps with changing magnitude. Then by finding the mixing weight or participation strength of those sensors in the observation, we can discover groups of those observation sequences. So in addition, we can also further discover the correlation of groups of those harmonics. In this case, these two signals are generated by the same sensors. And fingerprints generated by the discovered by PLiF or CLDS method can correctly identify those frequencies of group of harmonics and their mixing weight. So again, this is the result of clustering by using the PLiF method, where we can produce very meaningful patterns or meaningful features, while compared to PCA, its accuracy is pretty random. Well, we also tested this feature extraction method in the hierarchical clustering case, where we have 10 sequences of network traffic. It's BGP data collected from 10 routers in big cities in the United States. So we try to.
I have a quick question about the network thing. I can understand the walking motion and sort of a well understood physical dynamical model. What about, I'm not very familiar with this. Is the network traffic has very good intuitive way of explaining the underlying physical model?
Okay, that's a very good question. So does the data here, network data here, actually follows our assumption of the dynamical model? So because this data is from backbone routers in big cities, so our assumption is that there might be cases it's actually very common that those traffic going through multiple routers, but perhaps with some delay. So that's corresponding to the time shift I mentioned earlier. So our method of PLiF can actually capture that time shift, and ignoring that time shift, then can group those sequences with the same dynamics together. So by using the hierarchical clustering on the PLiF features, so we can group those cities in this way, and they are close to each other. This is sort of anecdotal validation of the method, and often those routers in nearby cities, perhaps they will have common traffic through each other with some delay.
So this looks very similar to wavelet analysis.
With what?
Multi-time scale analysis, right? That's essentially what you're doing. Wavelets or multiple time scale.
Yes. This is a multi-time series, multi-sequence analysis. Our PLiF model and CLDS actually are still multi-dimensional observation. So there are multiple sequences. Okay. So since this data is very large, we want our algorithm to be scalable, and we actually tested the walk clock time versus the sequence length, and it turns out that with different number of time sequences, the walk clock time is linear to the length of sequence, which is desirable. So another surprising result from the underlying model of complex linear dynamic system is we discovered that discrete Fourier transform can be viewed as a special case of CLDS. To see this, CLDS can learn the transition dynamics and the projection dynamics, but they are in complex value. By so if we enforce the transition dynamics to be a diagonal matrix with the multiples of the basis frequency, we can actually learn the projection matrix. And the projection matrix will be corresponding to the Fourier coefficient. And here are two plots of the Fourier spectrum over several synthetic data, and I believe by DFT and CLDS we can produce almost the same spectrum, histograms of the spectrum. So okay, that's all for the feature learning for time series. I'm going to give a brief summary of some other time series methods I proposed in the past. So again, to recap, I described three categories of data mining tasks, namely pattern discovery, feature extraction, and parallel algorithm. We have covered Dynamo, Bolero, and PLiF and CLDS. There are additional methods to handle different specific cases. For example, in this case, in this work, we want to solve the dynamical system in a scalable way. We want to come up with a parallel algorithm that can speed up the learning on multi-core shared memory computers. Well, we proposed a cut and stitch algorithm. Well, this is the plot showing the speed up of our algorithm and versus the increasing number of the processors. So we can see that with the increasing numbers, we can get almost a linear speed up up to some point. So another work is trying to find patterns from large scale unlikely streams and perhaps find anomalies. So our data is pretty big. It's 67 gigabytes with 1 billion clicks for 30 days. So interestingly, our proposed Windmine method can discover several interesting patterns. For example, on different websites, there are different access patterns by the users. For example, in job websites, we can observe this daily pattern. So every day, have some people looking for jobs, but in particular, there are spiky pattern on Mondays. So perhaps people are trying to look for a job on Monday, and then their interest will diminish over time. And then again, next Monday will increase. Also, for weather websites, there's a spiky pattern in around 4:30 p.m. My guess is perhaps everybody is trying to leave job, leave company, and getting home. Then they check the weather and check the weather conditions. Also, for the health website, there's some spiky pattern in the morning and during the night as well. So again, so these patterns are discovered not from the raw data sequences, because the raw data sequences is quite spiky, and often the small spikes are overwhelmed by the larger spikes. Instead, we decompose the raw sequences into a few meaningful hidden patterns, and then we can discover the spikes in the hidden components. So by doing that, we can discover those hidden spikes for different websites. Now back to our motivation scenario, where we want to monitor data centers and perhaps control the data centers in energy efficient way. So on the right shows some sensors we deploy at the data center trying to monitor the thermodynamics by monitoring the temperature, humidity, and also the workload of each server. So there are very complex cyber-physical interactions in the center. Here's one illustration. So on the floor, there are cold water coming in and coming from the CRAC, which is the computer room air conditioning unit. And those cold air will go through the servers, and then the hot air will come out from the ceiling and going back to the crack unit. Now we propose a model called thermocast, which models the different thermal quantities here, including the fan speed of the AC and the incoming air temperature, the workload on the server, the outcoming temperature, and the nearby servers as well. Then we put everything into a single framework, and by modeling the cyber-physical dynamics in the model. And our goal is to predict the temperatures based on the prediction of the workload and also the controlling of the fan speed and the incoming air temperature. So these are some results. We want to investigate two aspects of this algorithm. The question number one is, can thermocast accurately predict the temperature? It turns out that in our experiment, we use 90 minutes of data as training and then predict 5 minutes of the temperatures. And we can achieve 2 times better accuracy than the pretty straightforward method by auto-regression. And second question is, how long ahead can thermocast forecast the thermal alarms? Thermal alarms here means somewhere in the data center, their temperatures are going above the threshold. And we test our thermocast method against the baseline, which is by auto-regression. And it turns out we can predict the thermal alarms 2 times faster than the baseline. Okay, let me conclude my talk. So in this talk, I talk about several motivation scenarios where we can use time series mining techniques, including motion capture in game and movie industry, data center monitoring control, and environmental monitoring computer network. There are some applications in health informatics as well, which I didn't cover today, but we do have some ongoing work in this area. So the takeaway message is, for all the models I covered, including the Dynamo, Bolero, PLiF, CLDS for clustering, and also thermocast for data center monitoring. For all these models, the model-based approach can actually work. Those forecasting, summarization, segmentation, anomaly detection can be solved by a same model if we have the correct model. And also, if you have one good forecasting model, you should be able to do all the rest of the tasks, including summarization, compression, segmentation, anomaly detection. And second takeaway message is domain knowledge can actually improve the model quality. We have seen this result in reconstruction for the motion capture data with a bone constraint. And also, by incorporating the thermodynamics in data center models, we can achieve better prediction compared to the completely general model, domain knowledge-free models. So here are a list of the references sort of related to my talk today. And thank you all.